outstanding academic contributions, Professor Jiang was elected as the Fellow of the International Water Environmental Association. And also he is a director of the Research Center for Carbon Cycle Sustainable Technology and Assessment of National Taiwan University. And Professor Jiang mainly engaged in the research on the prevention and control of environmental pollution. He has focused on the generation and the control of disinfection byproducts in tap water, the development of advanced oxidation technologies for emerging pollutants, the absorption treatment of organic compounds in the air, the technology of the carbon dioxide capture and reuse. Today, he will give an interesting talk about the application of a high gravity technology for the reduction of various air pollutants and carbon dioxide mineralization. So let's welcome Professor Jiang.
Okay. Yeah. Thank you very much for Professor Zhang for your kind introduction. Of course, it's my great pleasure to attend the meeting. I try to show what I learned from the past 40 years in the university. As Dr. Zhang mentioned earlier, I graduated from Purdue University in 1982. Since then, I have been fully devoted to my research job in the National Taiwan University. Okay, so tonight I'm going to plan to show what I learned from you. Can you see my slides? Not yet.
No.
Oh, yeah,
so
probably.
Share screen.
Yeah. Probably you have to let me share my screen so I can turn on my slides.
I'm not the hoster. The hoster is Talk EEH. Can you give the? Okay.
Yeah, can you see that?
Yeah. I can see the slides now.
Okay, good. So my subject is fully focused on the air pollutant abatement and also the CO2 minimization. Okay, so you have to know why we have to focus on this subject, because the PM is a particular metal is quite important. The NOx, we call this are the criteria pollutants. The VOC is like a hazardous air pollutants. The CO2 mineralization and utilization also is quite important because that's a climate change issue. So we try to develop the one technology, see how we can solve the issues simultaneously. So last section, I try to let system be optimized. So we have to use the life cycle analysis based on the engineering, environmental, and economic analysis. So this is my outline, okay? I just mentioned to you the air pollution issues should be related to the energies, okay? So as you can see, that's the emissions could be generated from the power, industry, transportation, and the building, and so on. So the air pollutants, including the nitrogen oxides, particular PM, and the VOC, and even ammonia. So today I'm trying to demonstrate the high gravity technology. Sometimes we call this like a high G. Okay, so why this technology is quite important? So we have to go to the fundamentals, looking for the fundamental, the theory and the principle. So I believe all of you quite familiar with the so-called two-film theory, okay? So, this is a gas phase, the gas film, this is a liquid phase, the liquid film, okay? So the high G is typically, it's like a traditional technology, so-called the absorption tower. absorption tower, okay, and also the waste scrubber. So absorption tower is commonly being used for the gases pollution control, and the waste scrubber is kind of typical technology for air particulate control. So I believe the high gravity technology, high G, is kind of combinations of waste scrubber and absorption tower. Okay, so let me introduce a little bit the principle and the concept for all of you. So you think about the gases, comes from this side, and the liquid goes to this side. So this is the reactors, okay? But the reactors have very unique features because there's high gravity. So that means the gravity, the centrifugal force should be higher than the traditional one. Probably more than 100 times than the traditional gravitation forces. So this is called a high gravity. Okay, because of the high gravity, the centrifugal forces occur in these reactors. Okay, so it demonstrates a lot of the phenomena shown in here. As you can see in the reactors, in general, we can divide it into 3 zones, so-called the cavity, the packing zone, and the inlet zone. Okay, in the small spaces, okay, they cover a lot of natural phenomena in here. So for the chemical engineering, they might interested in the mass transfer, heat transfer, and for the mechanical and the civil engineering, they are looking for the fluid mechanics. So those are the fundamentals related to the high gravity technology shown here. Okay, so this is in this the reactors, this is in the packing zone. As you can see, they have a higher micro mixing, between the gas and the liquid in this zone. Okay, so the high Gs have a different operation mode as indicated in this diagram. So this is, you can see the liquid, it goes from the top to the bottom. Okay, then the gas from the bottom to the top. So this is so-called like the countercurrent, the process, the countercurrent, the flow, the mode. And this one is called a co-current. Okay, this is like the closed flow. Okay, so this is 3 typical operation mode related to the high gravity, the high G. So high G, sometimes you may call like high gravity rotating the pack bed. So they have a lot of benefits, which including they have a relatively high mass transfer and the low liquid hold up. They have a very high micro mixing efficiency in the reactors. So consequently, they have a very higher hydraulically and the frothing capacity. They have a better, the cleaner, the efficiency, the performance, have a relatively small reactor size. So this is the benefit shown in the high G's performance. Okay, the last one, we try to demonstrate, okay, the high Gs, they can control, they can reduce the level of the lux and the particular metals and the salts and even the carbon dioxide. As you know, that's the traditional conventional technologies try to remove the air pollution control. Okay, so you can see this is so-called a deluxe. This is called like a big house filter, electric filter, and then this is like a FGD process. It's so-called a flue gas destabilization. Okay, so the high G's the process could have the potentials. Okay, they can remove the lux, the PM, and the SOx, and even carbon dioxide simultaneously. So that's why we have the hope, have the wish in the future. If we can use the high G's, the technology successfully, probably we can, replace all the technology in here. But we have to be gentle, to be humble at the moment, because of the size of the reactor is not so big enough, can control the flue gas from the coal-fired power plant, but it could be used for a small industries like the electronic industries and some small steel mill industries. We have the experience. Let me introduce later, okay? And then the last one, I try to let you know why the G process can have such excellent performance, okay? So that's the mechanisms, that's the so-called green solutions shown here. As mentioned earlier to you, we call the air pollutants. In general, we can divide it into 3 categories, which including the criteria air pollutants, the hazardous air pollutants, the carbon dioxide is a typical as greenhouse gas emissions, okay? So the mechanisms for the control the air pollutants, for example, like the PM, okay? So should be have the mechanisms indicate the diffusions, okay, interception, and the inertia impaction, okay? For others, air pollutants such as SOx and the NOx, so you have to consider the phenomena, the principle regarding the oxidation and absorption, okay? And for the hazardous air pollutants, generally, I believe in the G process, they only consider as absorption, okay? If we introduce some oxidizing agents in the reactors, obviously the oxidation is going to be the dominated process, okay? So for the carbon dioxide, in my research work, will be focused on the absorption and the adsorption. So lately, I'm going to give you some information for our study in our laboratory, okay? So in order to improve, enhance the performance of the G process. So we have to plan to introduce some typical, the chemical is kind of oxidizing agent in there, which including the chlorine dioxide, the ozone, and hydrogen peroxide shown here. So you can see this is a typical chemical we can introduce in the reactors depending upon the air emissions enter into the G process. So basically, in conclusion, in summary of the theory shown in here, obviously, which including absorption, oxidation, adsorption, and so on, okay? So then I try to introduce a little bit about the reactors and some equipment in order to do the further study for the air particular metal. Okay, so this is the typical G process you can see here. This is so-called the cross current flow, the pattern shown here. In order to measure the air particular the performance, I believe all of you should be quite familiar with the module, okay, the Moody process, okay, so they can identify the different size of the air particular removed by the G process, okay, and in addition, we needed to provide the quality and the quantity of the air particulate throughout the particular generation. So this is the 3 very important equipment once you try to do the air particular control and some reduction, okay? So at the beginning, as I mentioned, we have to use in the Moody, okay, to identify what types of the size, the particle size distribution curve in here, okay? So you can see this is Okay, this is the aerodynamic diameter shown here. Okay, so this is relatively, that's a small particle shown here. You probably heard about the PM 2.5 and the PM and the nanoparticle. Okay, so you can see the particle size distribution, and this is accumulate the particle size distribution. So you can see what will be the averages or so-called aerodynamic the size. Okay, based on this information, we can determine the size of the from the air emissions. Okay, and once again, if you do wanted to do the study, I believe the liquid gas ratio is quite important. This is one of the major factors you have to be serious consider. Okay, and on the other hand is the rotation speed. Okay, this is the high G. In order to save the energy consumption, usually we want to have relatively lower rotation speed. Okay, but as you can see in here, this is the liquid gas ratio, and this is a different level of the rotation speed. Okay, so as you can see, if we operate the reactor quite well, usually we can have higher than probably the 95% the reduction of the air particulate. Okay. On the other hand, you try to estimate to measure the particle or particular the concentration as shown in here, the diagram. As you can see at the different level of the liquid gas ratio and at the different level of rotation speed, you can have the different performance. Okay, so that's the typical the data shown here. Then we try to introduce to you as some engineering, some data, the factor and the indicator to literally try to design for the reactor. So we have to using so-called high gravity factor in here. So this is the ratios between the gravity force and this is like a centrifugal force. Okay, so you can see the high gravity usually have a better performance here. Okay, so you can see this is different rotation speed, and you can get the relatively the different level of the removal efficiency and the different level of the particular concentration shown here. So the two diagrams, the two figures indicate the high gravity, the factor is quite important. Okay, then we try to explain to you. Okay, we can use the empirical the formula as you shown before. The liquid gas is important. Okay, and the high gravity, the factor, the beta also is important. So this is the empirical formula. Okay, so we can estimate the PM efficiency based on this empirical formula. Okay, so you can see this indicates how accuracies from our models prediction. Okay, so this is called the empirical formula. Okay, then we try to using the theoretical approach to give you theoretical the models which we can understanding the mechanisms why the PM, I mean the particular metal can be reduced and controlled by the high G process. Okay, so at the beginning, I just mentioned to you that high G have the packing materials, they have the film, and also they have a droplet. Okay, so you can see the overall the removal efficiency based on the PM removal. Okay, should be which is a function of the packing, the film, and the droplet. Okay, so lately we try to estimate, okay, the amount of the efficiency, okay, shown in here. Okay, so as you can see the models, the development. Okay, so first of all, we try to understand the basic the parameters indicates in the packing efficiency. This is like the film efficiency. Okay, so this is the two fundamentals formula shown here. Once again, you can see the liquid gas ratio is quite important shown here, and the other one will be the features of the RPB is the high G process and the thickness of the packing. Okay, so that should be related to the efficiency of the packing process. Okay, and for the film, you have to estimate the size of the particle diameter shown here. Okay, but on the other hand, you also have to estimate the thickness of the liquid film. Okay, based on those formula shown here. Okay, and once again, we have to estimate the amount of the droplet, okay, which can be removed through the high G process. So once again, this is the theoretical, the model based on this parameter, and this is the factor we can estimate the amount of the particulate removed by the so-called the drop the process. Okay, so you can see there's a series, the formula allows us to estimate. Okay, so once again, this is called a Stokes equation. Okay, so that should be very important related to the fluid mechanics. Okay, I believe you have understand about the Stokes law. Okay, shown here. Okay, so once again, if we try to estimate the overall removal efficiency regarding the PM removal, so you have to understand the packing, the fuel, and the droplet. Okay, so this is the fundamentals and the theory. Okay, so based on this formula, we can estimate the amount of PM can be removed by the high G process. Okay, so once again, we can see this is the different particle size distributions from the different the test. Okay, you can see this is the original data, but we can using the model, which quite successful to predict the performance, as I mentioned earlier. So once again, I believe the model development throughout this investigation, which have been successfully, can predict the result. As you can see, the accuracy is very, very, very high, and the error, is very, very low, as you can show here. Okay. Then second, the subject we are trying to talking about the why the lux can be removed through our high gravity process. Okay, so before you try to understand this principle theory, okay, you have to go back to understanding the absorption and the oxidation, the process. Okay, so I will explain to you. Okay, so that's the only difference, from the PM remover and the lux remover. Okay, the mechanism, okay, is quite different. Okay, for the lux remover, you have to be seriously consider about the absorption and the oxidation. Okay, so this is the two mechanisms shown here. Okay, so this is the general the diagram let you know how we can run this experiment. Okay, so as for this experiment, we introduce the two or three different the chemical. I believe the chlorine dioxide and the ozone, that's the two major chemical for the oxidation process. We call this is the highly oxidizing agent. But in order to control the level of the pH, so we also introduce sodium hydroxide, okay, and the sodium sulfide in there to see the performance. Okay, I will tell you later. Okay, so at the beginning, we try to do some absorption and oxidation, the process, okay, shown here, okay. So as C told earlier, so we introduced the different levels of the chemical in there, okay. So this is like the sodium sulfate, this is sodium hydroxide, and then this is the urea, and then this is the sodium carbonate, okay. So you can see the different performance, okay, because of the different types of the chemical, okay. So in general, that's a lux removal has following the sequence, okay. So there's a sodium hydroxide, there's a sodium carbonate, there's a urea, there's the tap water, okay. But you know, the best removal is about 30 ppm from the 200 to 170. So I believe this is didn't provide the better performance. So that's why we try to introduce some oxidizing agents in there, okay, showing here. But before we try to understand the remove efficiency regarding different types of oxidizing agents, you have to recognize there's some NOx, okay, the chemical component in so-called the nitrogen oxide. You can see there's a different the chemical species, okay, shown in the nitrogen oxide. That each of the chemical species, they have different solubilities, okay. That should be based on the Henry's law and the Henry's constant shown in here, okay. So if we have the higher Henry's constants, okay, that means we have a relatively higher solubility. So consequently, you might get the higher performance as we can, okay. So this is a very important message, okay. But once again, from the combustion process, the nitrogen oxide should be including so-called fuel NOx and the thermal NOx and promote the NOx, okay. But in this research work, we just concentrate on the NOx generated from the chemical industries, okay, not from the combustion process. So that means the different chemical species, okay, in the nitrogen oxide will be dominate for the performance, okay. As you can see, this is the typical the concentration file at the different time, okay. So here, so you can see that chlorine dioxide have a relative performance, okay. So you can see there's a relative low level, okay, less than probably 30 ppm, okay, the concentration shown here, okay. Then we try to improve the performance of the oxidizing agent. So that's why we adjust the pH value. Also, we introduce the different types of the chemical associated with the chlorine dioxide, okay. So you can see this is the chlorine dioxide versus the sodium sulfate, okay, have a better performance, okay. Under this operation conditions, okay, we have a relatively higher removal efficiency of the oxide could be achieved higher than 95 percentage, okay. So this means the sodium sulfate, cooperates with the chlorine dioxide, have a better performance than that of sodium hydroxide and sodium hydrogen peroxide, okay. So then we try to explain why this process, the high G, have such a better performance. So we have to go back to check the major factors, so-called the the HTU is the height transfer the unit. This is the area of the transfer unit. Okay, so those are the major parameters. Okay, for the engineering, the scientists, they use those two parameters to evaluate the performance of the nitrogen oxide and any gases pollutant reduction in the reactor. Okay, so you see, as you can see, this is by using the chlorine dioxide with the sodium sulfite, you can see we have a very, very small of the HTU and the area of type unit, okay, a transfer unit, okay. So if you can see there's a smaller HTU and ATU, obviously that's have a very excellent performance, okay, because of this technology, okay. So in comparison with other research scholars, okay, so in our research work, you can see we have demonstrates a small the size of the HTU and the ATU, okay. So that means we have a better performance because of using a small of the unit, okay. Then we have to expand, okay, see how we can estimate the amount of the NOx removal, okay. So once again, you have to go back to realize to understand the overall mass transfer coefficients with respect to the gases phase, okay. So once again, we have to go back to the literatures, okay, to know those are the major dimensionist group, okay. So that's the major the numbers you have to be understand, okay. Then using the data, okay, then we fit this the model so we can estimate the mass transfer coefficients based on this is a formula, okay, shown in here, okay. So if we have this formula, if we can estimate the mass transfer coefficient, then the based on this is we call the mass material balance, okay. So I believe the chemical engineering always using this is mass balance equations, okay. So we can estimate the air emissions, okay, throughout the unit process shown here, okay. So this is really just based on the material balance, okay, shown here. So once again, you have to know the mass transfer coefficient in here. So if you know the mass transfer coefficient in here, that's based on this theoretical formula. So we can estimate the amount of the concentration of the NOx oxide throughout the reactor, okay. So this is the boundary conditions, okay. So as you can see, this is the inlet concentration of the NOx, okay. This is the outlet the concentration, okay. If we can estimate the number, the values of the mass transfer coefficient, we can easily calculate that, okay. So this is based on the data, experiment data, and also the developed model, so we can see how the data can fit our model, okay. So once the model can be verified, so that you can, for the engineering, is much easy, allows you to do the air pollution control design, okay. And on the other hand, if you try to enhance the performance of the nitrogen oxide reduction, see if you know the mechanism, if you know the model, so you can have the preliminary study, okay. So you can see the our predicted the value and the data showing in the experimental work, which is relatively close. Okay, so that means we can using the high G process can be successfully to control of the nitrogen oxide. Okay, this is one. Okay, so once again you can see this is the process. Okay, this is the different the radius of the packing materials, the packing radius. Okay, so this is another data, another experimental work shown here. Once again, we can use in the preliminary develop the model. We can successfully estimate the nitrogen oxide concentration from the gas emissions. Okay, this is the inlet, the gas concentration. This is like the outlet concentration. You can see the models predicted quite well in here. Okay, then the third missions will try to demonstrate how the high-G process can be utilized for the VOC process. Okay, for the VOC control. So we just choose the two typical the VOC compound shown here. One is the trimethylamine. Okay, you see this is the significant for the human health. Okay, so they can irritate the lungs, okay, the throat, respiratory the tract, causing the losses, okay, and others adverse effects. Okay, and secondly, there's a threshold. Okay, there's an odor problem is quite important, but unfortunately for the trimethylamine is the threshold is very, very low. So I believe this is a very tough the missions for the environmental engineering. They really try to control the trimethylamine for the human health and also for the odors. You know, this is a public so-called public nuisance. So you have to realize the level of the VOC should be reduced to such accepted level. Okay, then the second the typical VOC is called IPA. Okay, it's isopropyl alcohol. Okay, so that's just kind of the problems, issues associated with the human's skin. Okay, so you can see causing lots of adverse effect on the human health. Okay, so this is why we have to be seriously concerned about the IPA. Okay, and as you know, for the electronic industries, they're using a large amount of the IPA. So either we try to recover, reuse the IPA on site. Otherwise, we try to reduce the IPA to a level which can be accepted from the aspect of the human health and the public nuisance. Okay, so this is the threshold for the isopropyl alcohol. Okay, so as you know, that's for the VOC controls principle. Obviously, have to be back to the Henry's law and the Henry's constant, because this is the kind of the absorption of the phenomena. Okay, so you can see this is the typical information associated with the IPA and here. Okay, then I try to introduce the technology and the experimental work to all of you. So you can see we try the several different runs, okay, experimental work in this study. So we're using the different level of the rotation speed and the different levels of the liquid flow rate versus the gases, and using the different types of the chemical and also the different level of the reaction times to do the experimental work shown here. Okay, so in the entire process, for example, if we generate, okay, the IPA, the VOC through the pipeline, okay, then we try to introduce the chlorine dioxide and the ozones in the pipe. So this is the we call the 4 stages for the gases oxidation. So that means the VOC already can be reduced through the piping, through the pipeline system. Then we inject the VOC and the chlorine dioxide in the high G process. Okay, then we have the absorption, the phenomena reactions in the reactors shown here. Then the step called the 3rd stage, that should be including the oxidation and absorption in the entire the high G process. So you can see and the whole reaction process can be divided into 3 stages, shown as is shown here. So we do believe the gas liquid ratios is quite important as the major factor affecting the reduction process, okay, shown here. So this is just a preliminary study by using the different the 2 types of the chemical agents shown here. One is the chlorine dioxide, okay, as shown here. This is the ozone, okay. So you can see there's a significant the difference, by using those 2 different chemical. So finally, we try to using the chlorine dioxide as a representative oxidizing agent in the following experiment work. Okay, so this is see by using the different the high gravity factor and the different levels of the gas liquid ratio. You can see we can get the different the results shown here. Okay, but we see the performance is not so good as I just mentioned earlier because of the natures of the TMA. Okay, so that's why we have to using the improve the performance of the high G process, and also we needed to add the different the level of the chlorine dioxide in order to improve the performance shown here. So you can see if you improve the performance in here by adding the hydrogen dioxide with other chemical, so they can have a relatively high performance shown here. So we do believe the chlorine dioxide, this is the good one. Okay, then we do several the tests in shown here. So probably we have run about 36 rounds. Okay, at the different level of the chemical the agent, at the different levels of the chlorine dioxide. There's a gas liquid ratios and the rotation speed shown here. So we can see the 22 to 24. Okay, that's the 3 runs. I believe they have relatively the better performance shown here. Basically, you can see the remove efficiency for the trimethylamine can be higher, achieved probably 99%. Okay, so by that times, by this situations, we can see the odor's intensity can be improved from the number 6 to number 1. So the number 1 means at this stage, at this rounds, under this rounds, I believe we have removed the great amount of the trimethylamines, okay, and also can meet the national emission standard. Also, in this case, I think the public concerns, the nuisance can be accepted, can be reduced to the level being accepted by the general public. Okay, then this is the performance shown here. Okay, then there's a better performance shown at the different level of the rotation speed and different level of the time. Okay, so this is just a repeat again as at the beginning. This is time we call measure for the trimethylamine, okay, removal. And this time we using the same techniques by using different level of rotation speed and the standard gas liquid ratio, try to evaluate the performance of the IPA. Okay, as you can see here, we have done a lot of experimental work. So you can see once we have relatively longer times and have a relatively larger rotation speed, we can have a better performance shown here. Okay, because time is not enough, allowed me to give you more detailed information shown here. I just try to summarize at the moment. I can see through the several tests, we can find this is the best operation performance. Okay, so as you can see at this levels of the operation experience, okay, we can get a relatively higher removal efficiency, have been higher than 96%. Once again, that's all those problems can be solved at this under this situation. Okay, so the last section I try to give you more recent research work deal with the carbon dioxide the issue shown in here. Okay, so this is the projects we have done more than 10 years. Okay, right now we're still working on this issue because the carbon neutrality and net zero is quite important. Okay, and my philosophy, my approach is just based on the environmental engineering. Okay, environmental engineering, just the questions how we can working on the material balance as shown here. This is based on the gas phase, this is based on liquid phase, this is based on the solid phase. Okay, so the solid phase, that means if we can introduce the alkaline waste in here, you know, the alkaline waste have some natures, okay, that can neutralize the solvent. Okay, also they have some absorption capacity which can absorb the carbon dioxide. Okay, and the liquid phase, that means you can use in the wastewaters if they have a relatively higher pH value, if the liquid waste containing the calcium and the magnesiums. Okay, this type of the cation the ions, I do believe they are going to play a very important role for the carbon dioxide reduction and for the carbon dioxide mineralization. So this is the gas, you know, coming from the stack from the different type of the industry. So my philosophy, if we can use the three different type of the waste from the industries, okay, if we can mix the three streams together, okay, obviously we can see the CO2 can be reduced to a certain level. And once again, based on the material balance, if the solid, the material can be converted to as a construction materials, so that will be quite successful. Okay, so for the previous study, we utilize this concept demonstrates in the China Steel Corporation in the company. As you can see the slide, the table shown here, we can really, based on our research work, you can see the carbon dioxide can be removed to the level 99%. Okay, so this is quite successfully for here. And this one, you can see this the liquid phase. Okay, you can see the pH value, you know, starting from the 12, then converted to the 6. Okay, and on the other hand, you can see the solid phase. Okay, you can see the free CaO at the beginning have a such a level, okay, have a such a amount of the free CO in here throughout the process. Okay, you can see that's a 0. You don't know why the free CAO is quite important. Okay, as a civil engineering, as a construction engineering, if the pavement, I mean on the road, okay, if you see the materials, if they containing as a small amount of the CaO, even less than probably 1 ppm and 1%. Okay, this kind of the concentration 1% and 2%. Okay, yeah, as you can see, if we put on the load, okay, then all throughout the weather, okay, called 风化, okay, very effect. Then the load will be not smooth. Okay, in some of the case, that will cause an accident because of the free CaO still being occur in the pavement, in the construction material. That would be very dangerous for the security concern. Okay, so if you can see by introducing the high G process, okay, in the systems, you can see we can have such a good performance. This is based on our previous operating conditions. So there's the rotation speed just in here, and this is the lower of the liquid solid ratio shown here. So based on the study, if we can utilize one terms of the steel making slag from the steel industries, so we can have the potentials, okay, I mean the capture capacity probably like a 1.1 55 tons. Okay, so this is a very good as a demonstration. Okay, indicate we're using the 3 different the waste, okay, put together, they have such a good performance. Okay, then we have to go back to from the theory. Okay, based on the thermodynamics concern. Okay, for the previous research work. So we have a lot of publication in this area. Okay, as you can see, this is from our study. We can figure out those chemical reactions based on thermodynamic study. You can see this is the energy we have to be provided, and this is the different process chemistry shown in here. Okay, so this is a very good one. And also, you know, we using the loading wastewater, okay, from the steel industries. Okay, so we have such a successful experience by using the wastewater and some waste, the chemical, the waste such as steel making slag. So we have a successful experience. Okay, then we have to looking for the reaction kinetic study. Okay, see the calcium, the ion the leaching process. And also we have to using the service coverage model, which can be successfully predict the performance of the carbonation process. Okay, so those are the based on the fundamental of the process chemistry. Okay, and that's because the alkaline waste, I mean, they have containing of the calcium, the iron. Okay, so the calcium ion can be reacted with the bicarbonate to produce the calcite. Okay, so that's why we have such successful experience. Okay, then the calcite can be considered as a green construction materials, can be utilized for as a cement blending or for other purpose. Lately, I'm going to give you more evidence indicate from the practical experience based on the data showing the results that could be used for the construction materials. And also we try to present the study based on the process chemistry, based on the reaction kinetics. So see all the basic, the fundamentals equation shown here can be explained the process very successfully. Okay, so you can see there's a different particle size of the steel making stack shown here. Okay, so that's all the heavy metal and some metals containing in the chemical in the steel making stack. In most of the cases, we worry about the leaching the process because we don't want to see the heavy metals can be leached, through our process. They are going to cause some secondary pollutions. It's not good for us to expect. But on the other hand, we try to maximize the carbon nature's capture capacity. So that's why we try to minimize the environmental impact. We try to maximize the carbon capture nature capacity. So that's why we have to do the further study by using the life cycle assessment. I will explain to you later. Okay, here. So this is the service coverage model. Okay, so that allows you to calculate the amount of the carbon dioxide that really can be converted into the calcite, okay, throughout the High-G process. Okay, so you can see lots of the parameter. This is under the different operating conditions. Okay, so we can have the different the reaction parameters based on the process chemistry, based on the service coverage model as shown in here. Okay, but on the other hand, we have to do the further study by using the sophisticated equipment. So that means the final product can be measured, can be identified by those the measurement. Okay, so by the SEM and the XED's equipment. Okay, so we can see the calcite and the carbonated the material showing on the slides. Okay, so this is see the calcite and some metal rich coal and those the chemicals shown here. Okay, so that's the first step. Okay, I mean the first step. Okay, so we can demonstrate. Okay, based on the materials, the balance, based on the reaction, the kinetic study and the leaching study, so we can see the carbonate has been removed throughout the High-G process. Then consider about the circular economies. Okay, see how the waste can be converted as construction materials throughout the High-G process. So the next few slides is going to demonstrate this construction. I mean, the waste can be successfully converted into the construction materials based on some international spec. Okay, so this is ASTM. I call those are the standard methods. Okay, that provide some protocol and some methods you have to follow up in order to compare with the benchmark. I mean also the standard. Okay, so this is the typical civil engineering training. So they have to test okay the materials based on the following the method and the spec as shown in here. Okay, so this is give you some information, so-called cement, the chemistries, okay, like a blended cement chemistry. So to tell you before, the waste materials by using the wastewater through the High-G process. Okay, so that really can be converted to such a supplemental cement. Okay. So based on the materials science study, as you see, there's some of the construction work, they really want to get so-called initial strength. So that means we want to get the the construction work, okay, should be finished in a few days, okay. So we expect at the earlier stages, then the construction materials, I mean the concrete, the materials, they have a relatively high strength, okay. But for the ultimate strength, that will be see as a traditional civil engineering, we're looking for the 28 days, okay. So once again, you can see the test, the age test time has a different the time. For some of them with respect to test at 3 days, 7 days, and the 28 days, and so on. Sorry about, take a few seconds. Okay. Okay, go ahead. So you can see this means the test should be measured at different times, because we have the different expectations for what the cement, the performance, okay. So we need to have an initial strength, that means goes to the 3 or 7 days, and the ultimate strength will be referred to the 28 days, okay. So then we have a autoclave, the sun-rays, the measurement, okay. So this is the very typical one, okay. You can see this is the one, okay. You can see this is based on our study, okay. You can see that's the CBOF means carbonate, the steel making slag, the carbonate, okay. The BOF is a basic oxygen furnace, okay. Basic oxygen furnace, okay, is a typical steel making process, okay. So this is the fresh, okay. That means the steel making slag already being accepted as considered as a construction materials. But if we can further utilize the steel making slag as good materials for carbon dioxide reduction, okay. So you can see we can have a better performance, okay, based on so-called autoclave, the sun-rays of the branded cement shown here. So, and on the other hand, I just say that's for the 3 days, 7 days, 18 days, 28 days, and the 56 days, okay. That's the Portland cement, okay, the level. As you can see, the carbonate, okay, that's our carbonate, the slag. They have a higher performance, better than the traditional cement. Okay, so you can see this is quite successful, and we do have the interpretation by using the cement, the chemistries can explain why the result performance have such a level of the higher level performance, better than the traditional the Portland cement, okay. And for the 7 days, okay, that's quite a depend, okay. In here you can see some at the different level, okay, of the cement additions, okay. So you can see sometimes we add 10%, 20%, 30%, okay. So you can see the different levels of the additions. You can see the performance will be have a little different. But anyway, in this slides, we can see if we want to have the cement have the earlier, the initial strength, okay, that's based on 3 days the measurement, okay. So you can see here we have a better performance than the cement, traditional cement, okay. If we consider about the regular, okay, the 28 days, okay, so I believe we still have a better performance than the cement if you see the curve shown here. But this curve is not good, okay, but we try to use good performance as we can. But for the durability, there's a kind of drying shrinkage. Okay, as you can see in this diagram, this is called the traditional Portland cement. This is the carbonate, the steel making slag. This is the fresh one. Okay, so we compare. This is three different levels of the measurements. Of course, we demonstrate the carbonate. Okay, the steel making process shown here still provide the better performance as shown here. Those are fulfilled with the STM the requirement, so we can have the maximum of 1.5 strength shown here. Okay, so that means we have already can meet the STM the requirement here. And once again, this is for the durability study, we can have such a better performance shown here. Okay, since the time runs very fast, I have to go quick as possible. Okay, so finally, I try to give you another information we have done from our lab. Okay, I believe all of you quite familiar with engineering, environmental, and the economic aspect and some evaluation. Okay, so usually I believe all the technology should be critically assessed from the viewpoint of engineering, environmental, and economic. And the questions how you can provide techniques, okay, and statistically you can integrate all the data throughout those triangles, the diagram. As you can see, this is like economic aspect, this is engineering aspect, this is environmental aspect. Okay, so this is the different the data. Okay, this is a standardization, and there is a weighting factor. Okay, so the question is just like a big data. So we have to have a data analysis. Okay, at the different the level, how we can put all the data together. Then you try to normalize the data. Okay, then give the different the weight. Okay, from the three aspects. Okay, then for example, if the technology variation throughout the 3E process, we can locate it in the diagram in the different level. For example, the zone 1, zone 1A and the zone 1, 2. I always tell my students it's like we take a plane. You are been lucky. You are be sitting in the first level, first class or the business class. So that's the level. That's the zone we really expect to be happen. Okay, in there. Okay. So once again, we try to put all the factors together, see how we can integrate them throughout this life cycle analysis. So see how the technology finally, once you evaluate, we can give the different zone as shown in this diagram, in this, okay. So this is the typical, the key performance indicator shown in this one. So this is the engineering, this is the environment, this is economic. Okay, for the environmental, this is our concern based on the life cycle analysis. So the different the software and the different the inventory data that always give you such an indicator. So you have to be serious evaluate. Okay, but for the economic study in this particular research work, we consider about the operating cost for capture. Okay, then we have to consider about the end product, the sale profit. For example, if we really can convert the waste materials being into the construction, green construction materials, obviously you can get some profit. Okay, and the third one, the waste treatment, the feed. As I mentioned to you, if we can use the wastewater, if we can use the waste materials, okay. So during the process, in some cases, we can neutralize the pH value, okay. So probably you can get some additional the benefits. The last one is very useful at the moment, is because of the C-band, okay, and because of the carbon, the price, okay. So you have a carbon right, you can get a carbon credit because of the international convention law. You can through up the carbon emission system. Sometimes you can get a carbon credit. So that question is how we can get the data to estimate the economics and to estimate the environmental impact based on the life cycle analysis. Those are the base of our research work, okay? So this is the very important message. Then once again, I believe in the back to the year of 1919, we started working on the life cycle assessment study. I still try to let my student understand there's a 4 key to success. So you have to be, first of all, to identify the scope of work of your research work. It's called a system boundary. And secondly, you have to let the data should be made locally available. Okay, the data inventory will be the second step. You have to be realize that. The third one, that's the model, how let you know how to predict your results. I believe the last one is the most complicated and the sophisticated one, is for the data interpretation. So once you get this information, that get the result, how you can explain the result and to make a right decision to the government decision maker or to the engineering practice, let them to make such so-called cost-effective solution. So this is very important. So once again, I try to briefly introduce what we have done for the past years. Okay, so this diagram gives you the scope work. Probably you're quite familiar with so-called BAU, is a business as usual. Okay, so you can see there's a 3 domain shown here. This is the I mentioned to you. This is like a solid waste, alkaline waste. This is like the wastewater. This is the air emissions. So you can see there's air, this is a liquid, this is a solid. Okay, there's 3 phases together. Okay, see how you can use that the waste materials throughout the process, through the hygiene process. Okay, so you can see there's a lot of unit process shown here. Later I will let you know. Okay, so this is the raw materials extraction. This is a process conversion. This is the product uses. Okay, so how we can use, okay, this is the hygiene integration. The process can provide some data that you know. Okay, so this is the very typical data. Okay, so that's been made available through our previous investigation. Okay, so as you know, there's usually we have a different scenario. Okay, we call this is low, this is the median, and this is the high. This is based on our previous research work. As I mentioned earlier, usually we have a relatively higher the rotation space and the different level of the liquid solid gas liquid solid the ratio. So we have a lot of different scenarios. So we just category as low, the medium, and the high, I just shown here. And this is the entire the hygiene process. Okay, shown here. As you can see, this is a grinding. Okay, this is a rotating. This is the pump. This is a blower. This is a this is stirring. Okay, this is a some of the unit process. Okay, just shown here. Okay, so this is called a carbonation in the process. Okay, and as you can see, this is the blower, this is the capture, carbonation, and the net carbonation. Okay, so this is the energy consumption. Okay, indicate the different percentages by the different unit process shown here. Okay, this is one. It's give you the CO2 emissions, okay, amount at the different the level of the unit process. This is because of the CO2, the sources, there's air emission, and this is the CO2, the sink. This is because of the carbon capture storage shown here. So this is very important. Okay. Okay, this is give you the different levels of the energy consumption and the carbon capture capacity, okay, shown here. So this is the carbon capture capacity shown here, okay. So, and lately we try to do the unit process, okay. So based on this unit process, you can see this is the business as usual, okay. This is the hygiene process. We expect that they are going to utilize such amount of the energy. Obviously, they are going to produce such amount of the carbon dioxide. That's because of the hygiene can, have a carbon capture the capacity, so we can get some emission. Okay, we can get some reduction shown here. Okay, so this is really because of the products. Okay, because the product can be considered as a cement material or the construction material. So obviously we can get some benefit. We can get some credits from here. Okay, so in summary of this study, so we can see that's based on the life cycle analysis. Okay, they usually provide such an analysis called the endpoint and the midpoint impact assessment. So because of the time is been limited, I don't want to explain in detail to you, but I believe all of you, if you can spend the time to understand the life cycle assessment, as should be based on the analysis. Finally, you can get an endpoint and the midpoint. Okay, so in here. So once again, I tell you based on life cycle data inventory, we have energy material use at the different unit process. This is the summary. All the process, all the equipment shown here. This is operating conditions, and all the information shown here based on our study, and also get some publications in the International Acrylic Journal. I can see here. So finally, as you can see, throughout the series study, we try to find the revenue, the gain shown here. Okay, so you can see this is the profit. We get carbon credits directly. Okay, directly, that means from the carbon capture. Okay, you can see this amount of the carbon has been reduced, been controlled throughout the hygiene process, and the credits that's been indirect. Okay, this is additional credits we can get from here, and this one is because we can reduce the water pollution fuel. The water pollution fuel, because we treat the wastewater, okay, throughout the hygiene process, so we can get additional profit shown here. Okay, this one is so-called the end the product, the profit, as because we utilize alkaline waste. Okay, at the beginning, this is the alkaline waste. Throughout the hygiene process, we can convert it into the green construction materials. So finally, it can considered as blended cement, as I mentioned to you. Also has been verified throughout the serious STM's test, so we can get some profit here. That's the cost because of the energy consumption, because of the chemical, because of the setup some unit process. So this is called the revenue gain. So we can get amount of here. Okay, you can see at the different the cases study. Okay, the A, B, C. That's because of the electricity, the price will be different. Okay, it's depending upon your government energy policies. You're using the coal-fired power plant, or use in the green and renewable energy, or even the nuclear power plant. So the price, the energy price will be different. That will be affecting the final result shown here. Okay, so I believe this is our discussion. Okay, so finally I just say I take evaluate all the potential technology and some through the scenarios. Okay, so we can find the H2. Okay, that's that means the higher intensity and the higher I mean the rotation speed, the higher the gas liquid. Okay, they really provide very good engineering the performance. Okay, that means they can have a relatively lower environmental impact and a relatively lower cost. So let's have a high engineering performance. So that's located at the that's a level. It's the B level. So I believe this is such a good, operating the conditions. Okay, based on the 3E measurement, 3E analysis. Okay, so I think this is quite a successful research study. Okay, based on our previous years, we really try to put the engineering practice and also the scientific, the theory, and together. Okay, so once again, we still have some the challenge. We have prospect in the future. So that's why I will take this opportunity, try to cooperate with other international students, see how we can working together in the recent future. So once again, we need to find the economic waste. Okay, this is the key to success. Okay, that's have you heard about the green supply chain and the waste to resources supply chain? And recently, I just put the supply chain as considered as a decarbonizing supply chain. That's based on the World Economic Forum. She mentioned about we needed to construction of the decarbonizing supply chain for circular economy towards the net zero the pledges. Okay, so that's one. And secondly, we try to do the process integration. So I believe the G is a good technology, but they still needed to work together because it's not the one-man department, it's not the one-man's the job. We needed to integrate the mechanical, chemical, and even electronic. Okay, that the process can be highly automatic. Okay, work. Okay, then your utilization, diversification is very important. Okay, see how we can utilize the waste. Okay, even throughout the study, you can convert the product as a construction materials, but the materials should be compared with the conventional technology. We're looking for the quality, quantity of the product, and we have to be evaluate the cost. Okay, so this is not an easy job, but from the principle, the theory, we have to improve our model development, see how we can generate the theoretical approach to the model. We can by integrate the reaction kinetics, the mass transfer, heat transfer from the chemical engineering experience, see how we can let the system become optimized. Okay, so the optimized study, once again, we have to based on the response service methodology, which is the statistical approach, and also some reaction kinetic study. There's a theoretical approach. Finally, have to be combined with the life cycle assessment. Okay, so finally, I try to do more integration for innovation. So see how we can have a waste, water, water, wastewater, and energy nexus. Okay, that's one. Okay, so the challenge and the perspective, okay, I just shown here. So we have to exploring the mechanism. Okay, we have to know the influence of the flow carriage risk. So once again, the full mechanical, the mass transfer, this is the typical, the scientific approach will be quite important. Okay, then we need to provide the data, okay, and should be not based on the laboratory data, should be put into the field to get more engineering experience that go to the international market, that the high technology can be considered as a proven technology, not just as a theoretical approach, okay. So we have to do some fundamental study, okay, through a serious model development and to get more scientific data to support the model development, because the model has been successful for the engineering purpose, for the engineering practice, and sometimes it's good for the government make a final decision, because of the carbon neutrality at the moment will be the bigger international issue. See how we can deal with the traditional environmental engineering issues and overcome the barriers of the carbon neutrality in the future. Okay. So once again, I just say the carbon, the high G is a quite successful experience based on the theoretical and the practical experience, but we still need to cooperate with the different engineering, see how that the system become more automatic. Okay, and so we needed to have so-called the internet ICA is kind of internet so instrument control and automation, ICA, and the MIS is kind of a management information system. So we have to cooperate with the information engineering, let the system become really optimized throughout the life cycle assessment. Okay, sorry about that. Take a longer time to bother you. I'm going to finish my talk. If you have any questions, I would like to respond to you. Thank you for your attention.
Okay, thank you, Professor Zhang. Very interesting talks. So everybody, I think everybody listened to a very interesting talks. So next question, next phase is Q&A. So for the, I think the Zoom audience already, and also we have the audience from the Bilibili, and I also log in with my laptop computers. So is there any audience has any come up with your fantastic idea or questions to ask Professor Zhang? Okay, so I may have 3 questions for this for this talk. So Professor Zhang, can I ask? So for 2 relatively, I think it's a kind of the open mind questions. So in terms of, I'm not familiar with the air pollutant control, but I'm a little bit familiar with the high G techniques, because recently our group, also many group members, are very interested in this novel techniques used in the heavy metal pollution control. So in terms of the future application of the high G techniques, can I ask, do you think what's the future fundamental research directions for this novel techniques for the maybe the air pollutant control? And this is the first question. And this I can ask the second together. In addition, compared to the current some popular air pollutants control technologies, can I ask what is the cost effectiveness of the high G techniques? I can say it make me notice that you mentioned you build some models, like you use the cost, engineering, and environmental impacts of the three balanced impactor to estimate the models. But do you think is there any other impactors of the? I also noticed you use the cost, use the 5 indicators, engineering 3 indicators, and environmental 8 indicators. So I mean, is there any connections between these impactors or the indicators? It make me a little bit confused. Make me a little bit confused because I'm not familiar with this field. And the last question is the third question is the life cycle assessment. I think this is the life cycle assessment is always important and critical for the future pollution control. I mean, if for the life cycle assessment for the, we also ask, I think many scientists ask what is the origin and how they transport and what's the final use and what's the annual use of some kind of materials. So is there any possibility to make any connections between these transportation of the NO for use products to this life cycle assessment, some models? Okay,
Yeah.
thank you.
Okay, so thank you very much for your 3 very challenging questions. I try to do my best to respond to you. Okay, starting from the last one, I told you before we starting working on the life cycle assessment study since 1990. So it's already been 30 years. Okay, at the beginning, we were working on this project, on this research work. First of all, we have to know how we can get the software. Okay, so this is very one. So right now, I believe you can quite familiar with the different the software provided by the different company. Okay, so if you are trying to working on the energies, the carbon dioxide, the greenhouse gas issue. So I would suggest the Umbutter. Okay, this is a good software. We bought from the German practice. That's been the 20 years. And in 1919, we have the model, the software from the Canadian government. That's called the Sigma. Okay, the Sigma approach. Okay, so you can see the recently, I believe the setup of the technology, I mean, the software could be have a 5, okay, different one. But no matter what the model that you try to use, we still being worried about what will be the scope of work. You have to be interesting one. And secondly, it will be the typical the data. You have to be using your locally available the data, okay? But if you don't have the data, you're using the international community through the data inventory, but that's good. But in most of cases, that can be represent to your personal care study. So, but anyway, this is the good for the reference. But I believe the last one is quite important. I tell you before, once you get the data, how you can utilize the outcome, the result to do the further study to expand your research work, and consequently you can expand to the government to let the decision maker to make a right decision. So I believe the data interpretation is quite important. Okay, so I believe at the moment we consider about the carbon neutrality. I believe this is a very good the message. For example, we consider about the VOC. Okay, the VOC, volatile organic compound. I believe for the environmental engineering, when they deal with the air pollution, the issue problems, I believe they spend their great efforts to try to let the VOC can be complete oxide, can be converted into carbon dioxide. So this is very good. So we can make the compound destruction higher than probably 99.99%. So for the engineering, for the environmental task force emissions, I believe you already achieved that. But unfortunately, if we consider about the carbon neutrality, I believe so-called the 典范转移，就是 shift the paradigm, the shift， 就是 you have to change the different philosophy. So by late times, the life cycle is going to play a very important role that you can consider your thinkings from the holistic approach. That means you have to consider all the different aspects from the engineering, from the environmental, from the economical, and the energy. So this is so-called life cycle assessment going to play a very important role by the year at 2050. Okay, so this is the message I try to leave to you. And secondly, we have to consider about your second questions mentioned about the benefits, the importance and the significance of the hygiene. As you mentioned about you're quite familiar with the hygiene principle and the practical in general. But the questions I just mentioned earlier to you, if the hygiene from the principle and the theory, they really can have the better performance to control the air pollution, okay, air pollutants, including the NOx, the SOx, the PM, and the carbon dioxide. So usually, the traditional technology for reduce the air particulates, we need to provide the cyclone, waste scrubber, the backhouse filter, or electronic EP, okay, electricity, the precipitator, okay. So this is one. And for the NOx reduction, we need to provide DLUX. And for the SOx removal, we have to provide flue gas destabilization. Okay, from the carbon dioxide, we need to provide the so-called post-combustion process or pre-combustion process and the oxygen combustion process. They have to including the carbon capture technology, including the absorption membrane and the chemical looping. So a lot of different unit process if you really consider of the multiple air pollutant abatement. But I believe the hygiene is going to play important the role, which can be safe, okay, the space. And we don't need to using lots different unit process on the manufacture for the air pollution control. So I just say we have one unity supposedly can replace all the recent technology. But I believe we still need time to verify this concept. Okay, but I told you before we already have this small scale data experience in the lab, okay, and we do have some demonstration project like the 大陆所谓的中试, okay, but the question is we don't have the opportunity to do the real things for the world, okay. But on the other hand, the hygiene also can be considered a good unit process for the wastewater treatment plant has already been successful by utilized in the chemical industries to remove the ammonia and others organic pollutants in there because of their the better performance for the physical chemical separation. So this is one. So I just say potential theoretical and the practical thinking from the previous research experience. I do believe the hygiene have lots of economical, environmental benefit. Okay, the first question you raised to me is quite important. What will be the future? We call the priority research direction, PRD. 优先值得做研究的方向 we call the research needs or the priority research direction. I believe we need to develop the relatively larger scale of the hygiene and to put into the practice that the technology can be continually running for a few months, okay, and throughout this practical experience, maybe you can provide more sophisticated sensor instrument in the field, in the unit process, okay, that the systems really can be instrumentation, control, and automation. And perhaps we can provide a good software in there. We can let the systems can be optimized, okay, based on the 3E analysis, 4E analysis, and while the life cycle assessment. Okay, thank you for your 3 questions. I do my best to respond to you. Okay, probably because the time is very short. Okay, probably the audience and the students may not can completely accept my proposal and my suggestion recommendation. But if you have any questions, please contact me. And if I have chance, I can go to university to to give you a serious lecture as I can. Okay, thank you. 谢谢大家哈，晚安，晚安。
Thank you, thank you, thank you very much. So thank you. Let's thank again for Professor Jiang today's very excellent talks, and wish you a good health and all the best. And I hope to see you in Changsha soon. maybe we can discuss this IG techniques in Changsha soon. Yeah.
谢谢谢谢啊，谢谢啊。Okay, see you soon. Thank you very much for all good friends and the students listen to the lectures in such at the the times. I know it's already 9:41. Okay, it's in the evening. Okay, so I wish all of you have a great success in 2023. Okay, thank you. See you in the recent future. Bye bye.
Thank you. Bye bye.
Bye bye. Bye bye. Okay.
唐主任，那我就下了。
谢谢张老师，再见。
唐主任再见。
辛苦张老师，拜拜。